Line arrays have dramatically improved the reproduction of sound for large audiences. The associated software has also evolved to a stage where the performance of complete PA systems can be comprehensively simulated. While this is already a huge improvement to the situation from before, arrays can still be optimized further to provide an even better tonal balance and level distribution. This goes beyond what is achievable with precise mechanical aiming alone and relies on the individual processing of every box in the array. D&B's approach to this technology is called array processing. To use array processing effectively, correct venue data and meaningful splay angles are required. The vertical dispersion of an array depends on its length and mechanical shape. It is also frequency dependent. This means that the tonal balance, or spectral distribution, and the level, or spatial distribution, cannot be completely consistent. This fact is visualized in the level over distance plot in ArrayCalc. The tonal balance is only consistent in areas where the two frequency lines are parallel. Mathematically, a solution can be derived that makes the tonal balance completely consistent. Let's investigate this for 3 example frequencies. To achieve constant level for a given frequency over the audience area, the array would need to have a specific mechanical configuration. However, to achieve exactly the same result, even for a neighboring frequency, the array's shape would have to be completely different. Obviously, a real-world array can only have one given mechanical shape at a time. Still, by applying complex FIR filters to each cabinet individually, the equivalent of the required mechanical shape can be achieved virtually. This purely mathematical approach has been tried, but the results did not meet our sonic expectations. Instead, the processing is calculated in a way that morphs along the array rather than making sudden and drastic changes. This means that the virtual shape of the array is transitioning smoothly between frequencies, resulting in the sonic footprint known from D&B. So, what is array processing actually doing? When a room model and the array designs are finalized in ArrayCalc, the array processing option can be enabled, which triggers the analysis process. The performance of an array is analyzed for a large number of receive points along all listening planes within its coverage. For every receive point, the sound of every loudspeaker is calculated across 240 individual frequency bands. The optimization process evaluates a predefined target frequency response, user-definable settings for level over distance, and processing emphasis. The result is a clever combination of FIR and IIR filters for each individual cabinet. This method keeps the additional system delay for array processing at just 5.9 milliseconds. So, what are the benefits and most important effects? With array processing, an array creates a constant tonal balance throughout its entire coverage with a user-definable level distribution. This is done by redistributing energy from areas where the sound is too loud to areas where more SPL is needed. Array processing also provides seamless compensation of air absorption at high frequencies. Array processing uses a general target frequency response for all arrays in a project, meaning that different arrays, for example main hang and outfill, will generate the same spectral result at the listener, despite having different length, splay settings, or even speaker type. Array processing adapts and evens out the vertical directivity, which can result in a more consistent direct-to-diffuse sound ratio and enhanced intelligibility, especially in reverberant spaces. Array processing improves the D&B line array system performance significantly and is the next level of democracy for listeners.